In physics, the Coriolis force is an inertial or fictitious force that acts on objects in motion within a frame of reference that rotates with respect to an inertial frame. In a reference frame with clockwise rotation, the force acts to the left of the motion of the object. In one with anti-clockwise or counterclockwise rotation, the force acts to the right deflection of a object due to the Coriolis force, and it's also called the Coriolis effect. Though recognized previously by others, the mathematical expression for the Coriolis force appeared in an 1835 paper by French scientist Gaspard Gustave de Coriolis in connection with the theory of water ripples. The Coriolis effect also describes the pattern of deflection taken by objects not firmly connected to the ground. As they travel to long distances around Earth, the Coriolis effect is responsible for many large-scale weather patterns, and it is the key to the Coriolis effect lies in the rotation. Specifically, Earth rotations faster at the equator than it does on the poles. Earth is wider at the equator, so to make a rotation in one 24-hour period, equatorial regions race nearly 1,600 kilometers or 1,000 miles per hour. Near the poles, Earth struggles at a sluggish rate. Let's pretend that you are standing at the equator and you want to throw a ball to your friend in the middle of North America. If you throw a ball in a straight line, it will appear to land the right of your friend because he's moving slower and has not caught up. Alright, this time let's pretend that you are standing at the North Pole. When you throw a ball to your friend, it will go to appear to land to the right of him. But this time, it's because he's moving faster than you, and you are moved ahead of the ball. Now, everywhere you play global scale catch in the northern hemisphere, the ball will deflect to the right. This apparent deflection is called the Coriolis effect. It is the fluids traveling across large areas, such as air currents, that are like the path of the ball. They appear to bend to the right in the northern hemisphere, and that is called the Coriolis effect. The Coriolis effect behaves the opposite way in the southern hemisphere, where currents appear to bend to the left. Now then, did you know that Coriolis effect has a connection with weather patterns? It's because such as cyclones and trade winds are examples of the impact of the Coriolis effect. Cyclones are low-pressure systems that suck air into their center or eye. In the northern hemisphere, fluids from high-pressure systems pass low-pressure systems to their right. As air masses are pulled into the cyclones from all directions, they are deflected, and the form system, a hurricane, seems to rotate counterclockwise. In the southern hemisphere, currents are deflected to the left. As a result, storm systems seem to rotate clockwise. Outside storm systems, the impact of the Coriolis effect helps define regular wind patterns around the globe. As warm air rises near the equator, for instance, it flows towards the poles. In the northern hemisphere, these warm air currents are deflected to the right, or which is east, as they move northward, and currents descend back toward the ground at about 30 degrees or north latitude. As the current descends, it gradually moves from the northeast to the southeast, back toward the equator. The consistent circulating patterns of these air masses are known as trade winds. Now to answer the question, how does Coriolis effect affect air travel? It is simple because of the Earth's rotation. Air gets deflected in the northern hemisphere. In the southern hemisphere, respectively, the air deflects toward the right and toward the left, resulting in curved pathways. That is called the Coriolis effect. That is all. Thank you for listening.